Okay. Okay, we start. Welcome. In the name of Argentine's SPE sections, thanks everybody for joining us today, mainly from Argentina and South America, but also from many countries around the globe. I am Juan Pablo Barrer, Program Chairperson of the Society of Petroleum Engineers of the Argentine section. It's an immense honor and pleasure to present this webinar entitled Geomechanical Processes Affecting Optimization of Multi-Stage Hydraulic Fracturing, of the illustrious global celebrity of our industry that generously accepted our proposal of being here today and to whom we are deeply grateful, PhD Mark Zoback. This conference program promotes the SPE's mission to collect, disseminate, and exchange technical knowledge, as well as to provide opportunities for professionals to improve their technical skills. The SPE thanks the companies and organizations to allow their professionals to serve as lecturers, in this case, Stanford University. We also thank the sponsor of this cycle of conferences of the Argentine section of the SPE. In the gold category, to Pan American Energy, Pluspetrol, and Shell. In the silver category, to Pampa Energía, Tecpetrol, YPF, and Equinor. And in the bronze category, to Halliburton and Industrias Juan F. Seco. We take the opportunity to remind the expected fourth symposium on exploration and production of unconventional resources to be held in Buenos Aires, Argentina on next March 2022 at Marriott Hotel, organized jointly by the Patagonia and Argentine sections of the SPE. In the coming days, you will receive an email with the link to access the video presentation of today's lecture on the website of the Argentine section of the SPE. Right away, I'll leave you with Fernando Tuero, Argentine's SPE officer and leading technical executive, who will be the luxury moderator of this webinar. Please go ahead, Fernando.
Thanks, Juan Pablo. Thanks very much. Hello, everyone. Hello, Mark. And we have a pretty large list of attendants. So I'm going to take a big breath and try to go through Mark's background, which is very extensive and very impressive. So Dr. Mark Zoback, he's the Benjamin M. Page Professor for Geophysics Emeritus at Stanford University, where he was also the director of the Stanford Natural Gas Initiative and co-director of the Stanford Center for Induced and Triggered Seismicity and the Stanford Center for Carbon Storage and senior fellow in the Precourt Institute for Energy. Dr. Zoback conducts research on in-situ stress, fault mechanics, and reservoir geomechanics with an emphasis on shale gas, and tight oil production, as well as CO2 sequestration. Dr. Zoback served on the Secretary of Energy Subcommittee on Shale Gas Development and the National Academy of Engineering Committee that investigated the Deepwater Horizon accident. Oh, I wouldn't want to be there. He's the author of 2 textbooks and the co-author of approximately 400 technical papers. His most recent book, Unconventional Reservoir Geomechanics, was written with Arjun Kohli and published in 2019 by Cambridge University Press. His online course, Reservoir Geomechanics, has been completed by over 12,000 people around the world. It's not that I missed my language and said wrong the number. It's 12,000 people, okay? Dr. Zoback has received a number of awards and honors, including election to the U.S. National Academy of Engineering in 2011 and 13, and he was, sorry, 2011. In 2013, he was also awarded an Einstein Chair Professorship at the Chinese Academy of Sciences and received the Robert Berg Outstanding Research Award of the AAPG in 2015. He was the 2020 chair of the Society of Petroleum Engineers Technical Committee on Carbon Capture, Utilization and Storage, and 2021 honorary lecturer for the Society of Petroleum of Exploration Geophysicist. At the following link, more information can be found. Then we are going to give you a certain link that you can check on Mark's profile but I guess with all the recognition that I have just mentioned, I guess it's enough to have some envy at least. So I'm going to just give you some words about the abstract of the webinar. So there are going to be two topics addressed, which are fundamental to improving production from unconventional oil and gas reservoirs. The first topic is related to the viscoplastic behavior of clay and organic rich rocks. Through field data, laboratory tests, and theoretical modeling, we demonstrate that lithology-dependent layer-to-layer variation of the least principal stress are commonplace, where oil and gas are produced from unconventional reservoirs. These variations of the least principal stress occur because of viscoplastic stress relaxation, meaning that the two horizontal principal stresses become closer in magnitude to the vertical one, relative more viscoplastic formations. It will be demonstrated that variation of stress magnitude with depth have a dramatic effect on hydraulic fracture propagation and strong influences optimal well spacing and lateral landing zone. The second topic is shear stimulation during multi-stage hydraulic fracturing. Several case studies will be presented in which slip on pre-existing fractures and fault induced by pressure leakage out of the hydraulic fractures significantly affect the drainage volume around the well and has a significant effect on production. Using machine learning and AI techniques leads to insight about completion parameters that optimize production in a given area. Very interesting. So we are going to do only the questions after Mark finishes his lecture. So it will be like a Q&A space afterwards. And so I encourage you to do to write down the questions in the chat area that you will find top right on the screen. So it's even better because once you get a question on your head, you just write it there, and so then you don't forget it. So I will start compiling all those questions, and at the end of the talk, we are going to go through all of those. So I leave you now with the so much expected Mark Zoback. Please, Mark, go ahead, and thanks.
Well, thank you, Fernando and Paul, and it's really nice to be speaking to all of you today. Good afternoon, good evening, depending on your time zone. Let me share my screen and get started with the presentation. Well, as Fernando has said, this issue of optimization of production, of course, is of great interest to us as exploitation of unconventional reservoirs becomes more and more important around the world. The book Fernando mentioned, published in 2019, contains a lot of the fundamental principles that underlie my comments today. These are also covered in a course on edX, a free course on unconventional reservoir geomechanics. So there are two courses. This is the second one. But most of my comments today are actually going to be updating this. The book was published in 2019, the course about the same time, but we've made some really interesting progress in the last couple of years, and I look forward to telling you about that. And I include the references to the work as we go along, so you can follow, by getting the presentations, you can learn more. I'm going to go through a lot of material pretty fast, but again, you'll have a chance to learn more at later time. Of course, the motivation for all of this is the unconventional revolution that started in the U.S. in the Barnett Shale, basically in the Dallas-Fort Worth area. And when you actually look at the recoverable resources just here in the United States, these are equivalent to some of the largest oil and gas reservoirs in the world. And of course, you have tremendous unconventional resources in many other parts of the world, especially Argentina. But so these exploitation of these resources is really quite important. Now, this is from the textbook, and the point we were making here is what we we're looking at thousands of wells. Here's 12,000 wells in the Eagle Ford, broken into 2-year cohorts. Here's probably about 10,000 wells in the Bakken Formation, and this is oil production. And then in the Barnett and the Marcellus, again, thousands of wells. We break the data up into 2-year cohorts from different time periods. And what you can see is a common feature of all of these fields, and whether it's oil or gas, is the rapid decline of production as a function of time. If you look at cumulative production, the book there's a small error in the scale here in the book. This is corrected, but the cumulative production has increased as a function of time in these various fields as technology has improved. But the increase is modest, 40 to 50%. In the Marcellus Formation in the northeastern United States, there's been a dramatic improvement in average well recovery as a function of time. Now, of course, as we look back all the way back to 2000, some of this data goes back to 2005, the resources have changed in price, and the economics of unconventional development has been both very good. It's very good right now because oil and gas prices are high, but it's been very poor at other times. The operational efficiency, however, has increased dramatically. We can drill and complete the wells much more effectively today than we could, say, a decade ago. But also the level of effort has improved very dramatically. In other words, the wells are longer, the number of frac stages have increased dramatically over time. And the fact of the matter is, after hundreds of thousands of wells in North America, recovery factors are very low, on the order of 25% in dry gas and less than 10% in tight oil. And the expenditures are enormous. This was 2019 in the United States alone, and it was $80 billion. And so, we're leaving more than 90% of the oil behind. So we want to do better. Now, this is from a paper. I'll mention it again later. It was actually an undergraduate research paper we published at ERTEC in 2020, and it looks at the Bakken Formation. And if you look at, the cumulative oil production per well, and you look at 2-year periods, 2007, 2008, all the way up to 2015, 2016, it kind of looks like the average well has progressively gotten better, over this roughly 10-year period. But actually, if you look at cumulative oil production per foot, that's not the case. In fact, the first 2 years was actually better than the most recent 2 years. And what's happening here is we're simply drilling longer wells and doing more frac stages. But in terms of the production per foot, there has not been an appreciable increase in production. So I want to address these topics making 3 points. First is, get the stress right. You can't do geomechanics with the wrong stress state. And I'll point to several examples and come back to the Bakken in just a minute. Then I want to talk about, optimization of stack pay when there's multiple formations from which you can produce hydrocarbons. And I want to talk about this process of lithologically controlled variations of the least principal stress, this process of viscoplastic stress relaxation, and how it affects hydraulic fracturing. And I'll show you examples that are carried out in, with real data sets from industry through my collaboration with ResFrac and my collaboration with PetroAI. And then I want to address this issue of shear faulting and what happens during stimulation, and point to a couple of phenomenon you may find interesting. So let's talk about getting the stress right and start with stress orientation. Now, the map on the left is a recently published map of all of North America, published by one of my former PhD students, Jens Erik Lundstee, and I appeared in AAPG. And what we're doing is showing information about the orientation of the maximum horizontal stress. Of course, you can't, see the detail at this scale. We'll look at that a little bit later. And then the background color is showing you the relative stress magnitudes. So if we think about relative stress magnitudes, the most extensional stress state we can think of is where the minimum horizontal stress is approximately equal to SH max. They're both very low and much less than the vertical stress. Now, a normal faulting, we call this radial extension. Normal faulting is slightly more compressive. SH min is less than SH max, which is less than SV. Then we can get normal faulting and strike slip faulting going on together. SV and SH max are about the same and greater than SH min, and so on. So we can go from very extensional to very compressional. And as we do this, we use a parameter known as a phi, which is characterizes how compressive the stress is between sort of 0 and 3. And we use that on the color scale. So you can see the eastern part of North America is extremely compressive. Then we get into more of a strike slip and a strike slip normal stress state in the center of the continent. And then in some areas like the Delaware Basin, the western part of the Permian Basin, it's pure normal faulting. The reason we want to think about stress orientation, of course, and the magnitude of SH min is that hydraulic fracturing is always controlled by the magnitude and orientation of the least principal stress. We know this from first principles, and we know it from some of the first laboratory experiments that were done back in the 1950s by Hubbard and Willis that demonstrated that using a box full of sand and plaster of Paris and putting a little bit of force on their box of sand, you would get a horizontal hydraulic fracture when the least principal stress was the vertical stress, and you'd get a vertical hydraulic fracture when the least principal stress was the least horizontal stress, SH min. And we know that the rock strength becomes less and less important as the hydraulic fracture grows. And this is from my first textbook. But what it shows is that once a hydraulic fracture is over 1 meter in size, the fluid pressure within the fracture only has to slightly exceed the least principal stress in order for that fracture to propagate. The strength of the rock is only important, when we're creating a hydraulic fracture. Once it begins to propagate, we just simply have to be pumping at the least principal stress very, very slightly above it, and that hydraulic fracture will propagate perpendicular to the least principal stress. Now, in recent years, there have been a number of field experiments that, by the way, some of these figures are keyed to the figures in my textbook. This is a field experiment from the Eagleford. It's a ConocoPhillips experiment. Kevin Ratterman is the first author, and they use both coring and image logs in monitoring wells around a hydraulically fractured well. And what you're seeing here are hundreds of hydraulic fractures in these various these 4 wells, monitoring what was happening here in well P3. And these hydraulic fractures are all parallel to each other with very small, maybe plus or minus 5 degrees, and very much, in the SH max direction, perpendicular to SH min. Now, one of the really interesting things they found in these wells is that there are many more hydraulic fractures than perforation clusters, and we still don't really, fully understand how that happens. Some of the fractures are probably dominating the others. The proppant is controlled, probably principally by 1 or 2 hydraulic fractures from each perforation cluster, but nonetheless, first it confirmed what we thought we knew, and it also introduced some things we still don't understand very well. But the fractures are propagating perpendicular to SH min. And of course, that guides the development of unconventional development. When you drill in the direction of SH min, and you carry out multi-stage hydraulic fractures. You're expecting the hydraulic fractures to propagate perpendicular to SH min. Of course, from a given stage, there's a competition. There's the outer fractures tend to propagate more because they're not as constrained as the inner fractures. So that's called the stress shadow effect. And because we're using slick water, typically we get these microseismic events that show us where the hydraulic fractures are going, but actually represent very, very small earthquakes, slip on pre-existing faults that is triggered by leak off of the pressure in the hydraulic fracture into the surrounding region. And when we lay out the wells, kind of as shown, and you stimulate the areas between the stages, you can get a zone of stimulation and production. This is from the cover of the book and a paper by Alex Haxo and I. This is real data, real microseismic events. We've reconstructed the size of the patch that slips and the orientation. So those are the little discs. Of course, there's uncertainty in the exact location. So we know these things are existing, but their exact position is unknown. But as you can see, they basically fill in between the hydraulic fracture planes. And this is going to be important later in the talk, excuse me. But let me come back to a very simple principle, and that is drilling in the direction of the minimum horizontal stress so that the fractures propagate perpendicular to a well. Now, I had heard many years ago that drilling direction in the Bakken Formation didn't matter. And I thought, well, the guys who were saying this had drilled literally thousands of wells, so I assumed they were correct. But then they said, well, it doesn't matter because the two horizontal stresses are approximately equal in magnitude. And I knew this just wasn't true. And so I suspected that maybe drilling direction did matter. So this is Irfan Wastami was an undergraduate student looking for a research project one summer. And so we put him to work on this project. We used data from the public domain. We had 7,000 wells available to us, and the results are really quite striking. The Bakken Formation is mostly production in North Dakota here in the north central United States, right on the border with Canada. You can see here from our stress map that there's very good stress orientation data, and it's all pretty consistent, roughly north 45 east. And so we know the stress orientation, we know the well orientations. So are we, we're going to investigate this question, does well orientation matter? And we chose, here's the data I just showed you, and this stress orientation we're seeing in the Bakken is similar to what's seen further to the northwest in the Alberta Basin of Canada. So we chose an area in the Bakken here where two things, all the wells are pretty good. This is one of the core areas of the Bakken. And as you can see here, there are wells drilled in many different orientations, and the color of the line indicates how much proppant was used in the wells. So we have wells of many different orientations and different amounts of proppant. And what we found was really quite striking. When we look in the first case in this core area where we had 176 wells, and we bin the wells, plus or minus 10 degrees of being in the exact right direction, we see the wells that were drilled in the correct orientation producing 2 to 3 times as much as the wells that were drilled in the wrong orientations. So this is public domain data, and this is perfectly obvious. Drilling direction does matter. It matters a lot. And it matters regardless of how much proppant you're using. It's just a very, very important factor that was simply ignored when these wells were being drilled. If we look at all of the Bakken, and we look at 7,000 wells, and we restrict ourselves to looking at the first 6 years of of drilling and production, we still see the same thing. It's not as dramatic, but again, drilling in the right direction always matters, regardless of how much proppant you use. So using more proppant is better in this particular case, but regardless of how much proppant you are using, drilling in the right direction is much better than drilling in other directions. When you look at the last two epochs, the last 4 years, that effect goes away. And we think this is caused by the fact that in the last two epochs, the wells were disproportionately infill wells, whereas here they're, the parent wells, the initial wells, and we think that's what causes this. But nonetheless, this resulted in non-optimal, thousands of wells that were not drilled in an optimal orientation. And, it's a factor, a factor of 2 or even more. So it's a huge mistake that was made. Now, this is our stress map of the Permian Basin. The first version of this was published in 2017. And the Permian Basin, of course, is a very active area right now of unconventional development. Of course, it's traditionally a conventional oil and gas producing region. In the Midland Basin here, we see a pretty uniform stress state. SH max is about north 85, north 80 east. There's some small variations. The stress state is sort of a strike slip normal faulting stress state. In other words, SH max and SV are about the same, and SH min is lower. Here in the Delaware Basin, it's more of a normal faulting situation. SV is the maximum stress, SH min is the smaller stress, SH max is intermediate. But what we see here is a really strong rotation of the stress from more or less north-south. It rotates clockwise to more or less east-west, and then keeps rotating to northwest-southeast. And we really don't understand this very well, but the data, as you can see, is very good. Every one of these lines represents multiple observations in a single well. And so, the longer lines are, very good data and very small dispersion. The shorter lines are less data points, but still reliable. And it's very systematic, and we don't understand it, but we certainly can use it. But one of the interesting things, once again, is that, in some places, here's SH max and here are the well in green. These wells are drilled in the right orientation, but these wells, are not. These wells are not. These wells are not. And so again, it's a case in which, a lot of non-optimal development was carried out. Okay, very simple, but widely ignored with huge economic implications. Let's talk about the variation of S3 as a function of depth. And I want to start by talking about the HFTS1 site, Hydraulic Fracturing Test Site 1. A number of companies came together and they pooled their resources and they carried out this project and they shared the data, and then they recently released the data to the public. So we know the orientation of the stress. These wells were drilled more or less north-south, so they were drilled in the correct orientation. They were drilled at 2 different levels, and then there was this deviated well as shown. Both the upper and middle Wolfcamp are producing formations. Now, what Arjun Kohli and I were interested in is when you look at one of these wells, and this is typical of the well paths, they tended to be toe up and relatively horizontal, and then toward the heel they were relatively horizontal, and they built angle. You'll see more profiles that look just like this. I actually do not know why this particular trajectory was chosen. It's common, of course, to drill the wells toe up because you're gonna, put a submersible pump down, near the heel. So that makes sense. But why this particular geometry was chosen, I don't know. And one thing that was easy to observe is that the microseismic response near the toe and the heel were markedly different. These three stages near the toe, you got lots of microseismic events, and they extended very vertically, quite a distance here, 1,200 feet, almost 400 meters. Near the heel, many fewer microseismic events, and they without nearly as much vertical propagation. Also, when you look at the magnitude of the least principal stress, now these are mini fracs and defits that were made in these various, in the toe of these 11 wells, as well as in a vertical pilot well, which is not shown here. And what you can see is that the SH-min, the minimum stress, this is an area where SV is the maximum stress, the data vary quite a bit. SH-min is pretty low, not very much above the estimated pore pressure. Then you have a couple high values of SH-min, low values, high value, high, low, high, and it's varying quite a bit and seems to be rather enigmatic. I mean, is this just scatter in the data? What's going on? Here's another case. This is from Oklahoma. And what you're looking at here is a well path in the Woodford Formation. And again, it's a toe up well. It looks very dramatic here, but it's a matter of scale. So this well is about 4,000 feet long, but the toe is only about 40 feet above the heel. But what happens is the wells drift up into this clay-rich lithofacies here, and then they steer them down. Then the well drifts up, and then it gets steered down, and so on. So the well path is sampling these two lithofacies. When you look at the well and you look at the magnitude of the least principal stress, it varies, very dramatically. The red dot is the magnitude of the least principal stress. So it's moderate, low, moderate, high, low, moderate, and it seems to vary with the clay plus kerogen content as determined from a geochemical log in the well. When the clay plus kerogen is high, so is the magnitude of the least principal stress. When the clay plus kerogen is low, we get a low magnitude of the least principal stress. In this second well, it's a different trajectory, but they want to stay in this middle zone, but it drifts down and they steer it back, but they overdid it and then it came up here. And again, you see these strong variations of the magnitude of the least principal stress, almost, essentially equal to the vertical stress to quite a bit below. And again, we see this correlation between the magnitude of the least principal stress and clay plus kerogen content. And the important thing here is that if you were an engineer and you were just, looking at the shut-in pressures from various stages, you'd say there's quite a bit of lateral complexity, between the heel of the well and the toe of the well. But in fact, what is lateral complexity is in fact the sampling of different lithofacies by the trajectory of the well. In other words, in this cartoon, if the stress is high, low, high, we'll show you why that's happening in a minute. And the well path is, going between these three different formations. You're seeing, different stress states, but it's not lateral complexity. It's simply the layering as sampled by the well path when these individual lithofacies are not very thick. I should point out that, in some of these stages, the blue bar here indicates how much proppant was placed. And when the least principal, when the pumping pressure was so high here, they actually did not fully complete the well, and they were afraid they were going to screen out. And so, about half the stages here were not propped because of the high pressures. Okay, and so they were really worried about the screen out process. Now, why is this happening? Well, it's happening because of this process of lithologic controls on the least principal stress and this process of viscoplastic stress relaxation. Now, we came across this around 2010, 2011, when we started laboratory experiments on these different unconventional reservoirs. So these are conventional triaxial measurements in the lab. We have a cylindrical sample. We're going to deform it axially. It's under confining pressure. We're going to be measuring the strain and so on. But we did these experiments. We had very, relatively few core samples. And so we wanted to get as much information from every test as possible. So we, initially measured the stress strain behavior very carefully to get elastic moduli. And then before the stress, this is stress and this is strain, before the stress got too high, we actually stopped the loading process in order to monitor the time-dependent deformation. In other words, the stress is constant and it's straining as a function of time. I'll show you this in more detail here in the next slide. And then after we allow the sample to creep for a little while, we continue loading. We measure the strength of the rock. A fault forms, in the sample, and then we measure the frictional strength of the fault. So we're getting the elastic parameters, the viscoplastic parameters, the strength of the sample, and the frictional strength of faults all in the same lab test. And this is what we discovered, and we published our first papers in Geophysics in 2013. Hiroki Sone was my student. He's now a professor at the University of Wisconsin. And it became quite clear as we looked at these samples of different composition, a decade or so, some of these samples, we call them shales, but in fact, these are pure, almost pure carbonate, 80% limestone with a, maybe 15% or so clay plus kerogen. Other samples have, relatively little carbonate, but, 40 to 50% clay plus kerogen. And so what we see is just a little bit of creep when the samples have, very little clay content, clay plus kerogen, more creep when we have a little bit more clay plus kerogen, and a lot of creep when we had a lot of clay plus kerogen. So why, we might call this ductility or viscoplasticity, but what I want to show you is viscoplasticity is really equivalent to stress relaxation. And stress relaxation tends to increase the frac gradient. So here's another way of looking at these same lab results. If you look at one formation, the Barnett, and you look at a relatively low clay plus TOC sample, only about 7.7%, very little creep. If we look at something with more than 40%, we see much more creep. The Haynesville here, this is Louisiana and East Texas. Again, we see the same thing. Here in the Eagle Ford, we're actually comparing two samples with roughly the same amount of clay plus kerogen, but this is being loaded perpendicular to the bedding, and this is being loaded parallel. So these, like the elastic parameters, the viscoplastic parameters are anisotropic. We've gone through, a lot of theoretical studies and a wide range of lab studies. Again, all this is in the book. And again, you can see this is axial creep. The red colors are the clay-rich samples here, and the blue colors are the most clay plus kerogen poor. We wanted to be able to describe this creep mathematically, and we tried a variety of creep laws that have been published in the literature. And we eventually converged by doing long-term creep tests. So we've done them for as long as a couple of months, but this shows data that's 2 weeks, about 2 weeks in length. And we wound up using a creep law that had been previously published by other investigators and used to describe cement. Okay, cement and rock are not the same thing, but they obviously have similarities. And so the creep as a function of time is a function of two parameters, B, which is basically 1 over the Young's modulus, and then this viscous component N, which we would have to determine experimentally. So we did this, and it turns out if you plot the creep data in sort of log space, the slope of the line gives us N, and the intercept gives us B, or 1 over the Young's modulus. And mathematically, this creep law we used is what is in material science called a Kelvin model, a spring and a dashpot in parallel. But you can think of them in a rock as being just a whole bunch of these with little, micromechanical, stiffnesses and viscous components. That just depends on exactly where you are in the rock and the pore structure and the local mineralogy. Now, and that then gives us this creep law that fits the data very nicely, but we have to, of course, Young's modulus is easy to determine, but at first we had to, mathematically, we had to do the lab tests and mathematically determine N, which was difficult and unpleasant. But once we started to look at this, we said, well, is this law reasonable? In other words, we're applying a lab experiment to the Earth. And what would happen if we took these, values of B and N, and we actually said, okay, well, let's pretend we have a 50 megapascal load on a rock in the subsurface, and we let it creep for 100 million years. Well, the high values of N here, these are very creepy rocks up here. Okay, these are the high clay plus kerogen and the creepy rocks. And down here, these are the rocks that are pretty elastic, that hardly creep at all. And what happens, and this creep is accommodated by the closure of pore space. I'm trying to go quickly here, but the publications include the details. And even over over 100 million years, the rock would only creep about 2 or 3%. In other words, if the porosity was, on the order of 30%, you'd see a 10% reduction in porosity over geologic time. Well, that's no big deal. The rocks could creep that much, and it's sort of physically realistic. Now, and we did a number of other tests, which you'll see in a minute. So the reason this is important is this issue of stress relaxation. What do I mean by that is this is how we do the experiments in the lab. We apply a constant stress. Of course, you instantaneously get an elastic strain. And then in the more viscous rocks, you get a viscoelastic or viscoplastic strain as a function of time. In the Earth is straining extremely slowly. And so if you think about applying a constant strain, you would get an elastic stress, but then the rocks are it's like they're flowing, right? And the difference, what we mean by viscoelastic stress relaxation, is that the differences between the principal stresses then would disappear. So for example, you go down in the ocean in a submarine, and of course, water has low viscosity, and there is no differential stress. The pressure is the same all around you. And in a very viscoplastic material in the Earth, the same would happen. The three stresses would become more co-equal. So what happens to the stress as a function of time? So we went through this kind of same example. We apply a constant strain. We leave it on the rock for a very long period of time. In the elastic rocks, not much happens. We have 20 megapascals, 3000 psi of stress difference. But in the very viscous rocks, the high-end rocks, we're down to about 100 psi of differential stresses. So the stresses would tend to disappear. And these numbers are intuitive, and in other words, they're realistic to apply this kind of law to the Earth. And then we looked at, how is the Earth loaded through geologic time? Of course, we don't know that. And so we do some computations. We apply, all the deformation in the past and do nothing. We apply a constant strain rate. We do nothing and then apply the strain very rapidly. And these three plots are almost identical. And so we don't really need to know, how the Earth was stressed through geologic time to apply this. So let's now start thinking about applying these principles in the Earth. So we've seen that some of these rocks are more viscoplastic than others. So if you think in terms of geomechanics and a Moore circle, in a brittle rock, like a sandstone or maybe a limestone without much clay, in a normal faulting environment, we can predict what SV is and what SH min is for a brittle rock. And if we know the pore pressure and we know the overburden, we kind of know SH min or a limit on it. But in these more viscoplastic rocks, what I'm saying is that the stresses are becoming more co-equal. That would mean that the magnitude of SH min is increasing in these more viscoplastic units. So if it's only a little bit viscoplastic, as it is here in these kinds of rocks, then the SH min might increase only a little bit. But if it's very viscoplastic, right, SH min might increase quite a bit. And so this is an increase in the frac gradient in the more clay and kerogen-rich rocks, the more viscoplastic units. Now, we were working our way through this, about a decade ago, and I remembered some really old data that had always puzzled me. The States was very much concerned about running out of natural gas, and a lot of research was being done in tight gas sands. Okay, so, conventional sand reservoirs, but that had very low permeability. And they were experimenting with large-scale hydraulic fracturing in this multi-well experiment in western Colorado. So these are very, microdarcy permeabilities, and they were making all sorts of measurements of the magnitude of the least principal stress as a function of depth in these three wells. So what you see here is the pore pressure going up as a function of depth. That's the blue triangle. And one hypothesis is that this was due to maturation. And in fact, there's some coals and thinking that, pore pressure was going up because of ongoing methane generation, which is, interesting. But what really struck me, and which I never had a good explanation for, nor did anybody else for that matter, is that the magnitude of the least principal stress would vary markedly about whether you were in a sand, which are the yellow inverted triangles, or in a mudstone or shale, which are the red dots. And the great majority of the sands are representing, these are very reasonable values for the magnitude of the least principal stress, considering what the pore pressure is. But, we're seeing lithostatic, the SH min, or S3, is equal to the vertical stress in these shaly rocks. And so that as we go down through the column, the stress is going low, high, 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 low, high, etc. And this very strong difference between the shales and mudstones than in the sands, with these two notable exceptions. Okay, so very confusing, very, this is 1,000 psi. So large changes in the magnitude of the least principal stress varying as a function of depth. And suddenly, these old data that were so hard to explain became easier to understand. And so we've been looking at that, these variations now in terms of the difference between S1 in a normal faulting environment, that's SV, and SH min, which is S3 in a normal faulting environment. And one of the questions, that we were very concerned about is how did this stress relaxation process happen as a function of time and as a function of this parameter n? Because some rocks have very low n, are not very viscoplastic, but some rocks, 0.7, 0.8, 0.07, excuse me, 0.08 are things we were measuring in the lab. And what it showed us is that in these more viscoplastic rocks, that you could get, 80 to 90% of the stress relaxation in, periods of time that were really quite short, thousands of years to millions of years. And so it was really quite interesting that we could ignore geologic history and we'd get a lot of stress relaxation in a relatively short period of time in those rocks that were more viscoplastic than the more elastic rocks. Now, we took a look at these data and we said, okay, well, we haven't measured N, for these different formations. We don't know what it is, but could we sort of guess? And we had a correlation between Young's modulus and this N parameter. And so we did our first rough estimate and we said, okay, let's estimate N from Young's modulus. We know the lower bound, the least principal stress can't get below that, what's called the frictional limit, which is the difference between SV and SH min. And we actually used this correlation and we predicted this black line. And our uncertainty was the gray bar. And so Xiaoneng Ma and I published this a couple of years ago in the SPE journal. And we said, it's not great, but it sort of captures, the general relationship between rock composition and the magnitude of the least principal stress. We're predicting the actual data is higher than the prediction, but nonetheless, it predicts a high value of the least principal stress where high values were in fact measured. But now let's go back and now look at much better data, and we return to HFTS1. Now you can see all the wells that were drilled. You can see the vertical pilot well, and you can see this slant well. And now we come back and we look at these individual measurements made mostly in the toe of these wells, and then the other measurements were made in this vertical pilot well. And to make a long story short, what we show is that the intervals with low clay plus TOC here have low stress, and they're basically predictable from knowing the vertical stress and the pore pressure using normal faulting theory. And the higher stress values are always seen where there's higher amounts of clay plus TOC. That's this center panel right here. So we're arguing in a normal faulting environment in brittle rocks, if you know the vertical stress and you know the pore pressure, you can predict the magnitude of the least principal stress in the brittle rocks. And depending on the degree of clay plus kerogen, you would get a much higher frac gradient in these more ductile rocks. And obviously, the reason this is important is that this formation and this formation would be a frac barrier. If we were fracking this formation, the higher stress here would stop the hydraulic fractures. Or conversely, if we're fracking here, the fracs would tend to run up into the lower stress we see here, or the lower stress that's below. We actually, demonstrate this with respect to just, showing the more circles here that in a brittle zone, we're in frictional equilibrium. In the more ductile zone, we're not in frictional equilibrium. And when we look at the microseismic data, this is showing the microseismic data as a function of distance and time. This is where we're starting to pump. and this is, time after pumping, we would expect hydraulic fracturing to propagate out with a velocity, hydraulic fractures to propagate out with a velocity, something like this. And what you see is as soon as you start pumping here, because we're in frictional equilibrium, you immediately get microseismic events, right? Which makes perfect sense. In this zone, we're not in frictional equilibrium. SH min is much too high. And in fact, in this case, they had to pump for over an hour. Pressure had to build up before you were, generating the first microseismic events. So all very logical. Now what I want to do is transition to our most recent application of all of this. And this is from two papers, both published earlier this year. In the spring, Ankush Singh, a former PhD student of mine, published a theoretical way using artificial intelligence and machine learning technologies to actually show how we could apply this without laboratory experiments, just using well logs. Okay, and I'll show you the result of that. And then in this paper, which I gave at the last ERTEC meeting, I demonstrate using examples from ResFrac and PetroAI that these lithologically controlled variations of the least principal stress have a major impact on how hydraulic fractures propagate and generate what we call frac fingerprints. And I'll explain this term frac fingerprint in a minute. Now, the data that Ankush and I had to work with consisted of measurements, basically 17 measurements of the least principal stress, and each one was a defit done in the toe of the well. And then we examined each defit and we determined the magnitude of the least principal stress. And you see that here. And there appears to be just tremendous scatter. Now we're looking again, 1,000 PSI here, scatter over a very short range of depths of more than 1,000, PSI up here. Okay, so what's going on? If we blow up the upper Wolfcamp and the middle Wolfcamp, you still see the scatter again, what appears to be scatter. And if you blow this up some more, you can see the variation of the least principal stress. And again, over this is 7,000 feet, this is 7,200 feet. So over about roughly 100 feet, you see a pretty significant variation of just about 1,000 PSI. So, what's going on here? Well, what we did, and again, the paper explains the methodology, we took our equation for viscoplastic creep and we parameterized it in such a way that this parameter n would be determined from log data. And we used a whole series of logs that, might have been relevant, as well as Young's modulus, okay? And to predict the difference between SV and SH min. And then we used various kinds of analysis techniques. So, basically to make sure we weren't overfitting the data, okay? And these various statistical techniques are explained in the paper. And what we were doing is, of course, we were calibrating the model, and then we were also predicting, for another pad. And again, making sure we weren't overfitting the data. We would use geologic constraints. For example, SV was the upper bound, and SH min from friction was the lower bound. And what we found here is that it did a tremendously good job of predicting the data. So for example, the green is our prediction. And in fact, there are two predictions here using two different techniques, and they're basically right on top of each other. Now, you can't really tell here, but you see these high frequency fluctuations of the predicted magnitude of the least principal stress. Let me just say at the outset that if you throw away half the data, you can predict the other half of the data. And in fact, when we calibrate up here, we can predict this data point without even using the data point in the analysis. If we zoom in here to these data, what you can now see is that what looks like, scatter is in fact systematic variations of the magnitude of the least principal stress, caused by these variations of lithology from clay rich to clay poor intervals. And these variations of lithology are, occurring rather sharply. And so we get these variations. And when we blow up this interval in the lower in the lower part of the middle wolf camp, you see we can, these predictions are pretty good, and the lower values are predicted and the upper values are predicted. Now, why does this matter? Why do these variations of the least principal stress matter? Why is it important to document them and to understand them? And it's because the magnitude of the least principal stress controls hydraulic fracturing growth. And so I presented this paper at the ERTEC meeting with my colleagues at both Stanford. Arjun Kohli is my former student, Ankush is my former student, as well as my colleagues at Petro AI, Troy Ruths, and Brendan Hall, and at ResFrac, Mark McClure and Rowan Irvin and Malcolm Kinsing works for Henry Resources. And I'll explain what we mean by frac fingerprints in just a minute. And so we're going to use in the presentation and in the paper, I use multiple data sets, but I'm only going to talk about a couple of them today. But I urge you to check out this ERTEC paper. Well, I had the number on previously. I left it off the slide, unfortunately, but it was from the 2022 meeting. So let's look at hydraulic fracture growth. Now, what do we care about? Well, we care about whether the fractures are propagating outward or they're propagating upward, right? If they're propagating outward, that has a dramatic effect on well spacing. If they're propagating outward, the wells don't have to be as close together. If they're propagating upward, they do have to be close together. And we also care about where the proppant is going, right? Because that's ultimately going to control the, productive parts of the hydraulic fracture where it's in contact with the reservoir. And that's why we're using ResFrac. So this is just a generic slide. And this is ResFrac modeling that is actually applied to the HFTS1 data. So I'm showing here in color. So this is the stress profile I showed you before, but it's color coded. So the light colors, that's low stress, and the warm colors, that's high stress. Okay, so this is nothing more than the measured. Okay, so this profile here, this is not theoretical. These are the measured values of the defit from the defits, and we're simply color coding them. Now, A and B correspond to actual stages that were pumped in the HFTS1 experiment. C is hypothetical. So let's start with C. It's the easy one. C is a hypothetical hydraulic fracture that's in a zone of low stress with higher stress above and higher stress below. So what happens is the hydraulic fracture just spreads out. And then here the color is representing the propped aperture. And that's a very nice propped hydraulic fracture that's staying in zone. Everything is just as one would hope and expect. But in these two stages, which are not very far apart, they're only a few tens of feet, a few, 5 meters, 10 meters apart. They're not very far apart. At the depth of the stage that, shown here by A, we get a little bit of outward propagation below the landing depth, but a lot of downward propagation, okay? And that's kind of obvious because the stress is higher here than it is below. okay? And most of what is propped is below the landing depth of the stage, but you do get some outward propagation. However, in zone B, what happens is you mostly, again, get downward and outward propagation, but you get very little propagation at that depth, and you get some upward propagation, okay? So you get upward propagation and downward propagation. And so this is what we're calling a frac fingerprint. In other words, the exact shape of the propped area depends on how the stress is varying with depth and exactly where you put the landing depth. And it's giving us in these three cases, it's giving us markedly different results. And it has, a marked effect on your effective exploitation of the hydrocarbon bearing zone and the implications one would draw about optimal well spacing. And it's, not going to be the same, in areas of stacked pay, depending on exactly where the landing zone is. Now, let's switch to HFTS2. And this is a paper done by Exxon and ResFrac, and I think I'm an author of this paper, but the principal point of this paper is that in a vertical monitoring well, there was severe upward propagation of the hydraulic fractures that was documented by fiber that was installed behind the casing of this vertical pilot well. In fact, there's a little bit of downward propagation, but about 1,500 feet, if I recall, of upward propagation. Now, if you take the stress model for HFTS2 and you actually put it into the ResFrac model, this is a video, but I'm not gonna show the video in the interest of time. This is exactly what was predicted by the models because of the variation of stress with depth. Very severe upward propagation. Well, here it is, but I'm just going to go on to the next slide. So here's the stress profile that was a combination of the measurements and application of the viscoplastic theory. Here's two actual stages. And in both cases, we see this extraordinarily severe upward propagation of the hydraulic fractures because the stress is getting lower and lower. However, the value of having the ResFrac modeling is the fact that now you know where the proppant is going, and it is not going up. It is staying more or less at the landing zone. And in this case, that's what's really important, right? And any conclusions you make about well depth and landing zone, it should be based on that. Here's that first case I showed you used in the geophysics paper, that our first theoretical paper, where getting at N and applying the theory without lab measurements. And what's happening here is really interesting because these are two hypothetical, wells, because we don't have the well data here. But what they're predicting is that there's actually a lot of overlap between the producing zones, and so these would be two wells. This is which are really not optimally oriented, optimally located, because they would be both producing from the area above well B and below well A. Let me show you another way of doing this, and this is what Petro AI has been doing, using AI and data science. And basically, what we're trying to use is geomechanically controlled analysis of drainage volumes, okay, informed by microseismic data in part, but mostly controlled by the variation of the least principal stress to understand well placement. And I'm gonna speed up here and go a little faster. But basically, in this example, you can see the predicted drainage patterns based on the fingerprints, based on the exact landing depth, and the prediction of 12-month production, and the correlation with actual well production. After considering tens of thousands of potential drainage volumes, that correlation is really very good. And that results, this is an example for Henry, in which they were drilling a 5-spot pattern here, as shown, good correlation with geochemical tracers, that you could actually replace this 5-spot with a 4-spot. And it produced a little bit less hydrocarbons, but it was far more economic because you were only drilling 4 wells and not 5. Some other things that came out of this is that when you were trying to figure out what the optimal well spacing is, the optimal well spacing, as you considered different distances from the parent well, depended on which bench you were in, because of the variation of whether you're getting upward or outward propagation. So optimal well spacing is different for different benches. And when you're looking at what the maximum amount of proppant is, that also depends on the well spacing, on the which bench you're in. And again, in some cases, it really didn't have any effect on the in this case, either the production or the NPV, and in other benches, it did. So it's really important to really understand what's happening. The final thing I want to say about this, and I just to wrap up quickly, is, this is what we're doing today with the modern theory. What most people do is they use an old theory based on some work by Ben Eaton, but then they add all sorts of complex anisotropy, and I call it the extended Eaton model. Other people call it the Poisson's ratio model. They add arbitrary amounts of tectonic stress or strain. And if you make the model fit, here, well, it doesn't fit up here, it doesn't fit down there. This model just does not work, but has been used many times and in many places. Let me wrap up really fast and talk about fractures. Of course, small-scale fractures are ubiquitous. They have highly varied orientations. And in the book, we show data from horizontal wells. And what you don't have are patterns of fractures parallel and perpendicular to the current stress state. What you do have are fractures that have been introduced into the rock over geologic time. When you stimulate that, you can make many of these fractures slip, and that microseismic cloud represents, stimulated rock volume, and you're creating pathways for hydrocarbons to flow. And if you actually look at these production data and you plot it in log-log space, what you find is, that the production is flowing off as time to the -1/2, or, in the ARPS equation, you get a B factor of 2, okay? And that implies linear flow with nearly constant permeability. Here's a paper by John Lee and a student, showing basically the linear flow for the first couple of years of production. And that's what we're talking about here. But what we're talking about is it's not only the area created in the hydraulic fractures, but it's also the microseismic area. Because, for this fracture to slip, fluid pressure had to come to this fracture from the hydraulic fracture and make it slip. Once you make it slip, then it's permeable, and the hydrocarbons can come back, to the hydraulic fracture. So this fracture network is very important, and that's what Alex Haxo and I described in this geophysics paper in 2019. Now, linear flow is, the flow rate's proportional to 1 over the square root of time. The proportionality factor is the area in contact with the low permeability reservoir. And of course, the matrix permeability is very important. And that's sometimes called an A square root of K model. And the sobering thing is that when you look at, realistic permeabilities for these rocks, whether you're looking at gas, which is shown in red, or the oil, which is shown in black, the hydrocarbons don't travel very far in a few years. And so it's really quite sobering that you've got to create permeable area as close as possible, because the hydrocarbons can't flow in these 100 nanodarcy rocks very far. And Lei Jin and I showed this through some modeling. This is all, a theoretical well, a theoretical hydraulic fractures, some theoretical natural fractures. But when you put this into production using, realistic parameters, you get like a halo of depletion around these permeable planes. And so I think the reason shear stimulation is important is that you're creating surface area, which is, critical for successful production. And so you really need to consider both the flow directly into the hydraulic fractures and the flow into the shear fracture network, which then eventually gets to the hydraulic fracture when you're thinking about these models. Because of this network, now we're looking at a gun barrel view of a Midland Basin case. You can see the wells. Every dot is a microseismic event. There's hundreds of thousands of microseismic events. We ascribe them to a particular well by its proximity. And basically what we're showing is that the larger the area of the shear fracture network, the more production they're in. And so the takeaway message here is that the microseismic cloud is doing more than just telling you a little bit about where the hydrofrac goes. It's actually contributing to production quite a bit. But you can't just draw, a volume around all of these hydraulic fractures. And the reason you can't do that, and why this traditional SRV definition doesn't work, is because the volume encompasses a lot of formation that's not being produced because it's too far from a permeable plane. But when you see these competing models, all of which might fit a production data, you can see models that are based on various either theoretical models like this kinetics model here, or this was another paper by Craig Cipolla. You can often fit these models with a wide range of geometries, as long as this A and square root of K are if you adjust them both, you can fit the data. So there's a lot of uncertainty, but my basic point in this is that they're both important: the area of the propped hydraulic fractures and the area represented by the shear fractures. I'm gonna skip over this just in the interest of time, but I will point out that we showed in a theoretical study where we have an image log, and we know the orientation of the fractures. We know the stress state, so the fractures are shown here. We know the stress state, and we predict when you're hydraulically fracturing, which fractures will be slipping, and then which ones will be not slipping, because you can never get, the net pressure is only a little bit higher than the magnitude of the least principal stress. And then we do what are called focal plane mechanisms. We take the bigger microseismic events and we figure out how they slipped. And then we actually go through the same analysis again. And what we can see is the microseismic events and the prediction from the image log are giving us very similar results. So this idea that the microseismic events are small earthquakes, magnitude -2. These are extremely small events, but they are in fact representing slip-on faults, which if you have an image, small fractures and faults, which you have an image log, you can actually see. We went through the same thing again in the HFTS data set, and we learned exactly the same thing, that you can actually predict what's going to slip from the image log, and when you have focal plane mechanisms, you get basically the same answer. So skip this last part and make one final point. When we think about larger scale faults, those faults have an architecture, and this is some of our own work, but other people have reported this too. You've got the principal slip zone, and you may get a fault gouge. Adjacent to the principal slip zone, you get a damage zone of multiple fractures, which kind of locally increase the bulk permeability. And as you get further from the fault, you get into the host rock and sort of some background level of fracturing. We see the impact of these fractures and faults all the time. This is 4 wells in Oklahoma. Here, these microseismic events are exactly what one would expect for a hydraulic fracture, except that this whole area was lighting up even when, well D over here was being stimulated. And so we actually think there's a normal fault cutting across the wells near the toe. And you can actually see some of these faults when you look at the 3D seismic data, as well as some strike slip faults, which is exactly what one would predict. This is the Barnett Shale. Here, the image log showed a concentration of natural fractures here, which we never understood why it was so concentrated. And later, we saw, in fact, there was a fault here coming through, and we saw actually this fault controlling the microseismic events from when this well A here was being stimulated. Here's another example. We saw these lineations in microseismicity independent of analysis of 3D seismic data, which then showed these faults. And what we see here is, in fact, some of these permeable damage zones are hijacking the frac job, and all the fluid is going events went here, but it was actually being controlled by the presence of this pre-existing fault. We'll see here. So I went through a lot of material quickly. I tried to include the references as appropriate, but we're, as an industry, we've traditionally done a poor job of optimizing production from hydraulic fracturing. Geomechanics has a lot to contribute. Geophysics here has a lot to contribute, and it's all closely linked to optimizing, the position of wells, the spacing of wells, and the fracking procedures. And it's through that integration, I believe, we're eventually going to make dramatic improvements in productivity. And with that, I'll thank you for your attention, and I'll be happy to answer any questions as best I can. Thank you very much.
Thank you, Mark, for your presentation. Very interesting. Some parts escaping my knowledge, but we have some interesting questions, I guess. Let's shoot them out and go to the chat. I go chronologically, maybe. I mean, I have one that it's more general. It says, like, I have knowledge that, for example, in the lower Vaca Muerta, in the typical target called the Cocina, has high TOC and probably high quartz content. So how does that affect the viscoplastic behavior, and what should be taken into account for the completion and design, etc.?
Yeah, well, I've done a little bit of work in Argentina, and the kitchen has always been of great interest. Because of the high clay plus TOC, one would think that there's a lot of viscoplastic deformation, a lot of stress relaxation, and that the frac gradient is going to be very close to the overburden stress. It's also possible in those cases to get horizontal hydraulic fractures. And the one thing I've never done is I've never actually had the opportunity, and I hope some of the people listening have the opportunity to really examine, the geometry of hydraulic fractures. We've seen horizontal hydraulic fractures in this, in the Marcellus Formation in very high clay-rich zones, because if there's no difference between the three principal stresses, then things like bedding planes become very important, right? And you can propagate a fracture along a bedding plane. So it could be that there are either horizontal hydraulic fractures or vertical fractures, which are then probably, if you're pumping at close to vertical stress and you are getting a vertical hydraulic fracture, a lot of upward and downward propagation. So I'd be very, very concerned, and small things could have, a huge impact. And so I'd pay very, very close attention to the magnitude of the least principal stress. That's going to tell you, right, is it the overburden or is it not? And the resultant geometry of the hydraulic fracture. Is it always vertical like it is in most places? Or in this special case, are you getting horizontal fractures in some cases?
Well, at least the simulations I have seen and the design that the service vendors, etc., show every time, they supposedly predominantly vertical, but yeah, you might be right.
I think it needs to be looked at very carefully, and I'd be very careful about just applying the models that the service companies have used in other places and just assume to be correct.
Well, yeah, that's something else too.
Well,
well, there's Juan Carlos Hernandez. He asks, I totally agree with creep deformation. What do you think when people use elastic equations where strain in the SH max direction multiply the Young's modulus and make that hard rock have a higher SH mean than soft rocks? In the end, the model shows that hard rock have higher principal stresses. Do you consider the methodology and conceptual a mistake?
Yeah. So anyone who's taken my my basic reservoir geomechanics course know that I really don't like this model that's commonly used based on an elastic assumption of instantaneously applied overburden and then arbitrarily added horizontal stresses. What's interesting is that when you look at unconventionals, that model, as the questioner implies, is exactly opposite. That traditional model predicts higher stress in the stiffer rocks. Viscoplastic relaxation shows you higher stress in the more viscoplastic rocks. So it is 180 degrees away. And so I think that model, should never be used, but it's especially important not to use it when it's being applied in unconventional reservoirs. So,
okay.
And I showed you one example very quickly of what I referred to as the extended Eaton equation not working. It really should not be used.
All right, thanks. The other one is short, but what are the lower and upper bounds on SH mean and SH max means in different fault regimes, and how can we find them?
Okay, in my first book, I talk about that a lot. And in the paper, the AAPG paper, published in 2021 by Jens Erik Lund-Snee and I, we actually show how to do that for different stress states and different pore pressures. So if you know something about the pore pressure, and you know something about the relative stress magnitudes, in other words, if you know what color your map is, following the system I showed you, you can actually put bounds on the lower bound and the upper bound for any stress state. And I know the Vaca Muerta is a strike slip but relatively compressional stress state. And, you know, in that case, you can actually predict the upper and lower bound for the stiff rocks. And then the degree of viscoplastic stress relaxation would make the three stresses more co-equal in the viscoplastic units.
Okay. There's another one. How can we find the approximate density of a formation when we have the weight percentage, different components and component densities?
Well, you know, that's sort of a standard petrophysics. You know, you can use a density log, or you can use a mixing equation, right? On mixing in the individual components. I think using a lithodensity tool or something like that's probably the best way to do it.
Yeah. It seems something here. My question did not get posted. Okay. There's a guy that posted something, but then at the end he put it again. Okay. From what I hear in your excellent presentation, looks like you believe in microseismic, but looks like the industry now really not observing the value of it.
Yes.
I hope this is not sponsored.
Well, first of all, I don't work for any microseismic company, so
good to check.
Let's make that clear. And I don't work for any 3D seismic company either. And I think, you know, every project, you don't need microseismic data in every project, and but you do need it in carefully controlled experiments to have a better idea of what's going on. And I'll give you, you know, in one example we published for the Marcellus Formation, we can clearly show that where we predicted you could get horizontal hydraulic fractures, the microseismic showed exactly that. Where we predicted you would get vertical hydraulic fractures, the microseismic showed exactly that. And so the problem with the microseismic industry in general is for many years they have promised too much and they have delivered too little. And, you know, many companies have just really felt that it was not of economic value to them. And so I'm not telling a company, you know, how to run their business, but I am saying that there are questions that can be answered with microseismic data that can't be answered any other way. So in specific cases, when you're, you know, if it's like a science pad, right, and you're collecting more logs than you would normally collect, maybe you're doing a little coring, investing in a good microseismic survey could be very, very beneficial. You don't have to do it all the time, but you do need to, you know, answer some of these really important questions, right? Because it affects a lot of decisions you're going to be making. So in a limited sense, I highly recommend it, but I don't mean to imply that you need it in every case.
Okay. Then this last one, I would say, where are the micromechanisms of creep elucidated? You mentioned reduction of porosity, but there might be other mechanisms. Along the same line, your figure showed delatency. How do you conciliate that?
Okay, well, the latency is only important when you're at very high stress and approaching failure. So that's general, you know, usually our stress levels are much lower than that. So we're not breaking intact rock. So let's take that off the table. The mechanism by which the creep is occurring, we know it's represented by a reduction in pore space. However, how that actually happens, we don't fully understand. So for example, you know, you have porosity in the structure of clay minerals. So it could be the compression of the clay mineral itself. Some of that compression, that time dependent, could be actually, you know, the intergranular pores themselves. The kerogen will often have porosity inside the kerogen.
Yeah.
So it could be the kerogen collapsing. So there are different mechanisms. They're all related to a reduction in porosity, but it's a very good question. And in different rocks, you know, it may manifest itself a little bit differently. And we tried to use some micro CT data, to investigate the rocks and try to actually see that. But in the end, we never really, it never really worked out. We never could really see it, but we tried. But it is associated with a reduction in porosity, and that porosity reduction could occur in different ways.
Okay, I have one other question. It's quite general, but I guess it's very interesting for everyone. I have seen operators sometimes label some areas with faulting or echelon type faults associated, and they associate that with higher risk. That's a higher risk of having trouble with the well, or it's because you have shown that maybe it's a useful. I mean, it could be beneficial sometimes, but if you can avoid the troubles with the well, then it could be beneficial, or no.
Well, I've been asked this question many times, and if you've got a good 3D seismic survey and you've mapped the faults, right? And your well path is going to cross one or more faults. I've been asked, so what do you do? Okay, well, if induced seismicity is a problem, induced seismicity during hydraulic fracturing, if that's a problem in the area you're working in, then the recommendation would be to skip some stages close to the fault, because you don't want to induce earthquakes, right? And we've seen other cases in which slip on the fault has actually damaged the wells through aseismic shear. So having a good fault map tells you that you might want to skip stages. If induced seismicity, is not a problem, what I would recommend is when you're close to the fault, do a small hydrofrac. Go ahead and perforate it, pump a little bit to connect the well to the formation, but you don't have to do a full stage, okay? Because that's where the fault might take all the fluid, and you may not get a successful prop fracture anyway. So that's the value of the 3D seismic data. When induced seismicity is a problem, you want to avoid right? And that's because the fluid is being channeled along the pre-existing damage zone.
Okay, we have a small cut, but I guess Juan Pablo is back in the screen, and I guess that means that we are late.
Okay.
So thanks very much, Mark. Very interesting. I would love to see that presentation again with some time, more time.
Run it in slow motion. It was my pleasure. Okay.
Thanks very much.
Mark, was very nice to have you here. Very interesting presentation. And well, in the name of the Argentine SPE section, it's a great pleasure and honor to award this certificate of recognition to today's remarkable lecturer, Mark Zoback. To you, Mark. And through this simple but appreciated detail, we want to thank and acknowledge the outstanding conference given, extended to Stanford University for allowing this spread. It is a really great privilege for us to have you virtually today, forever grateful. And thanks to our great audience. We hope you can also have enjoyed this webinar. Well, thanks, Mark. Thanks, Fernando, and thanks everybody for being here today.
All the best. Thank you. Bye-bye.
Okay, bye-bye.
Bye-bye. Pleasure. Ciao, ciao.